Good morning, all. So today we'll go through LSTM to classify 20 newsgroup dataset. Before that, we will quickly look through what LSTM RNNs is. So LSTM stands for long short-term memory. Now, why we are using LSTM? Because standard RNNs have poor memory. Like when we say long short-term memory, it's basically it remembers the information from previous state as well, right? So this was not happening in RNN. Like after um, maybe like after 1,000 iterations or so, it will not remember the previous information. And the reasons for this, like having poor memory, is a transition matrix which weakens the signal. So what so instead of having this transition matrix, what you want not instead of, but since this transition matrix is weakening the signal, what we need was a structure for which dimensions doesn't change over many steps, right? Like dimensions remain same, and this is the problem which is addressed by long short-term memory RNNs. So what is being done in LSTM is to have a complicated update mechanism of internal states, like uh, the hidden states which we are having in RNN. The update mechanism of that hidden state was made complicated in LSTM. So we can see that in LSTM architecture also. I'll show that. And by default, it remembers information from the last step, right? So you can see here. So like this is a state, cell state. This is previous cell state, this is new cell state, and it has to go through this complicated updation method, right? So, and this is the output, right? HT minus 1 and HT. So this is what we are talking about here, uh, about update mechanism of the internal state. Okay, so we have output, we have cell state, we have input, right? And then the cell state changes in two stages. So here there is the first stage for the cell state. Here there is second stage for cell state to change, right? So this is the complex updation method for cell state, right? And these two update methods are, first one is to decide what to forget, right? uh, like what information we should be taking from the previous state, and what new information to be added to the new state. Right. So this is what is happening in the forget state. So previous state is getting a matrix multiplied by previous output and input. So these two are combined here, previous output and input, and this is passed through a sigmoid function, right? And that is going through a matrix multiplication. So sigmoid function, the output of sigmoid function will be 0 and 1, right? So this sigmoid function will decide what should be passed here from the current input, right? Sorry, from the current input, yeah, from the current input and previous output, right? And then it will be matrix multiplied by the previous state, right? Uh, okay, and here in the add new information state, like this is forget state, and this is add new state, right? This is forget phase, and this is add new phase to the state, right? So here what is happening is the input again ht minus 1 and xt will be will be passed through a sigmoid function and a 10h function, right? Will be multiplied here, matrix multiplication, and then it will be added to the previous information, previous state, okay? And then this is what we are getting in output. Okay. uh, yeah, so this is element wise multiplication. This star is element wise multiplication. So this is my final output, a final new state actually, right? So new state is going through a forget gate and through a new gate, right? Forget the old and add the new. Okay. Yeah, and then we have final stage where the input and the previous output pass through a sigmoid function, and it is matrix multiplied by the state, the updated state, after passing through a 10h function. So here we are doing transformation. It is like uh, it is not activation, okay? Like it's transforming the data, transferring the state using 10h, and then matrix multiplication the uh, with the output, this output here, and then this is what we are getting as an output. Okay, fine. So this is how the cell will look like. This is one cell. There will be many such cells, right? This is one LSTM cell. These are uh, multiple multi-layer or not multi-layer but multi-cells, right? If you have more than so if you can have this as one, then there could be another LSTM as well. Those will be like multi-layer. And so this is most common version of LSTM. You can see other versions as well: gated recurrent uh, unit and depth gated RNN. It has more parameters than plain RNN, just because we have uh, this gates as well, right? In LSTM we call it as gates because and that is why like we use sigmoid and 10h uh, functions, activation functions, rather than ReLU, right? Because sigmoid, the output of sigmoid will be between 0 and 1, and the output of 10h will be between -1 and 1, right? And as it is said that most of the big performance improvements in NLP have come from LSTMs and not plain RNN. So LSTM is what to say, one of the most used RNN and uh, Yeah, you will see a lot of applications of LSTM in time series or in machine translations or in uh, uh, yeah, like even for question answering also, or chatbot as well. So there are many applications of LSTM. Now we'll quickly go through. Now we'll yeah. So this was summary of LSTM, and now we'll quickly go through classification of news group. Right. So so these are 20 news group data set. Right. Right. And so the data size, training data size is 1131 11,314, and the test size is 7,532. There are 20 categories. So these are all 20 categories. Okay. So, and what we are doing is we will be needing two things. One is the data for this 20 news group, right? And the glow data, right? Glow data is very much, it's basically a word vector, right? Or I would say uh, uh, word embedding, right? Okay. And so here we'll see the basic libraries which will be used for building a LSTM model. So first thing what we are first is like this pre-processing, which will from where we'll get this sequencing of the text. Then the model we are defining is sequential. The Keras supports two kind of models. One is functional and one is sequential. Okay, we had seen functional APIs and sequential API as well. So we are using sequential API for building the model. Okay. Then there are layers. So dense layer, embedding layer is what we are going to use. Uh, then we have a LSTM layer. Right? From sklearn we data sets we will be fetching a 20 news group. Will be loading to this fetch 20 news group data. From Keras we are going to use tokenizer as well. Right? And sequence, yeah, we will be having a pet sequences. Okay, so pet sequences is basically for if we have more than uh, a particular length of sequence, then we'll discard that sequence, or if the length of sequence is less, then we will pair it with spaces. Okay. So maximum features we are defining as 20,000. So this maximum feature is basically the number of words which we want to use as our input, right? So basically, given the text of this 20,000 news group, we'll be only taking 20,000. 20 news group data will be only taking 20,000 input features, right? And sequence length 30. Like if so, uh, yeah, we have to see like how this data is, but like we are restricting our data of size 30 only, right? Batch size is 32. Now let me, and then here we have niche group, train and test, length of niche group, right? Maybe I can show you here this niche group. What object is it? Okay. data, and let me see the keys, data and values. Okay, and other things, and target. Let me see what is there in the target. Okay, target is talking about one of these news groups, and data is talking about this. Let me see in data. Okay, yeah. So this is how the data is, right? And maybe I can. So from Gayaku, let final call summary. Final call for SI clock reports keywords is six. Hit sinks hours of usage functionality. Let me see key of this. Uh, this was in bunch keys. Okay, oh, sorry, not key but target. Target is 4. So okay, it is talking about some hardware. Make hardware. Right? Yeah, seems it is correct. Like correct means uh, I mean like it seems to be related to uh, hardware. I'll just try with some more data points. Yeah, this also seems to be for hardware. Okay, so this is what we have. Let me try one last one. Weapon of mass destruction. Hmm. Okay, it is talking about Middle East politics. Okay. Uh, Actually, there could be multiple classes as well. But yeah, we are looking for uh, a single class, right? Uh, Either 16 or 5 or 4 or so. We are not looking for 16 like this. This paragraph can be can be part of mm, uh, politics, or it can be part of guns as well, right? So we are not looking into multi-class. We are looking into uh, one class, right? Like one class means one label and not multi-label. Okay. So what we are doing here is now we are tokenizing it, right? Uh, and that will here we are specifying maximum features, which is like 20,000 number of words, right? And that will fit on the text data here. We can see the output of this for not for all, but maybe for just for this data. And I'm making it one. That was a simple sentence. It was easy to check. Okay. Okay, so from the tokenizer, I am, yeah, like I'm fitting this tokenizer on this text data, right? And then I am using this tokenizer to create a sequence data, right? So let's do this, and cool. So we'll just see this quickly. Okay, data one. Okay, my sequences are here. Yeah, so this is what I got for my sequence 10. I will just remove this, right? So basically, it converted this text data into sequences. Okay, I should not have done that. That is list of. Okay, I wanted to check. Yeah, this is list of list, right? So there are those all the training news is converted into sequences. So this is first sequence. Mm, yeah, from here the second sequence is starting, right? And first word is 14 because it is always from, right? Sorry. Now word index. So yeah, so word index is basically from this tokenizer, how many uh, unique words we got from this text, right? So that is what we are going to get here. So it is 134,142 unit tokens, right? We had taken every word from here, and here we are uh, here we will be truncating uh, these sequences about training and test data to sequence length, right? So basically we'll be having mm, we'll be having in one sequence we'll be having 30 the length of the sequence will be 30. Okay, now maybe I can show you. Yeah, this is train. Okay, this will give the length of total. Maybe if I do this, this is 30, right? I'm getting Y train and Y test as well from using Keras utilities, and we are going to use Glow data. I downloaded Glow data from this website, NLP standard, uh, nlpstanford.edu. Yeah, So from here you can download this data, right? So we are looking for this Wikipedia 2014 gigabytes 5 6 terabyte glow.6b .zip data. These are pre-trained word vectors. Okay, and you can train. You can also create. You can also train train your own word vector. So we have Wikipedia, we have Twitter as well. Right? So we'll be using this directly. Right? So I downloaded the data, and in the data file there are different versions of it. So 100D is like 100 dimensional word vector. For each word there will be a 100 dimensional vector, right? Length of that vector will be 100, and that is what I'm using. There are other variants as well, like 50 dimensional, 200 dimensional, and 300 dimension. Okay, we can change this to, let me see what, no, okay. um, I'm not sure if you will be able to see this, but yeah. So I have 100, 200, 300, and 50D, and I'm choosing 100D. Right? And now here, what is happening? Like for for line in F, like whatever I'm reading here, right? I'm splitting the line, getting the values. From values, I'm getting the word, right? And for I'm getting coefficients as well. Uh, so basically, uh, maybe I will not be we should not be printing everything, but maybe I can print this particular line, or not line, maybe these values, right? I'll stop it in between. Yeah, so this is how it will. I'll stop it. We'll just see this data. Okay. Yeah, I stopped it in between. Right. So okay, it got stuck. Yeah. So for the word the, like I'm having this data in this format, right? So these are all word vectors for word the. Then for comma, these are the word vectors. Did I had anything else also? Yeah. For off, these are the word vectors, right? For two, these are the word vectors, and so on. Okay. Um, since the data is huge, uh, I'll I'll just remove this print statement and will override this space. Okay, it's still running. Okay, it stopped. I'll just run this. So what we are doing is, for each of the words, right? For each of the word, we are getting that word, and we are getting all the coefficients, right? And we are creating a embedding index. It is a dictionary. Like for word, we are having all of those coefficients, right? And there are these 400,000 words, right? Which we got from glue dataset, right? Yeah, and we can see here a dog vector. Like for a word dog, this is what we have. We can change it to anything, like right? So let me change it to a dog again. Yeah. Now here we have we have now embedding indexes, right? Now what we are creating is embedding matrix, right? So first we are embed like the embedding matrix we are uh, so basically we are first putting zeros to the whole matrix, embedding matrix, right? And now we are looking into word index, right? uh, Word index item, which we got from here, right? We got this word index which is 134 142. So for each of these words, right, we have to create a embedding matrix, right? So for word and I in word index dot items, embedding vector, right? So we are creating one embedding vector, and that embedding vector we are actually getting it from embedding index. So for each word, right, for each word in word index we'll search for this here in uh, in this embedding index, right, and we'll get this data, right? So basically out of 40,000 400,000 words, we want only for this many words, right? 14142, right? So yeah, so this is what we are getting here, right? And for if it is not there in none, sorry, if this word is not there in the word vector, we'll use it, we'll have all zeros, okay? Right? And all zeros are already there here, right? So if it is not none, will sorry, if it is if embedding vector is not none, like if we are able to find the embedding vector, we'll add it to the embedding matrix, and finally we'll get this embedding matrix of this size. So these are 134,143 words and 100 word vector, right? Okay, so here we got embedding matrix, right? And this embedding matrix we got from Wikipedia, Glow data. So this is how we can use Glow data. Okay. Now, now coming to LSTM layer. So LSTM has units, which is like number of hidden states. Then activation 10H, recurrent activation, hard sigmoid. Uh, we have all of this information for here. So structure is very much similar to simple RNN, right? Units define the dimensions of recurrent state, and kernel refers to the transformations done on the input. Okay, and recurrent refers to the state aspect of LSTM. Okay, so yeah, so basically LSTM is divided into two parts: kernel and recurrent, which is what we are having here. Kernel and recurrent, right? Okay. Word dimension. This is the word vectors which we are getting from uh, a glue, right? Then we are defining a sequential model here. Then now we are adding different layers to it. So we have first layer is embedding layer, right? Here we have a number of word, sorry, the size of the input, right? Then word dimension, which is coming from here. Then weights are directly coming from embedding matrix, right? Okay. Input length is the sequence length, which is 30, right? And trainable is false. So which will basically which means that it will be using only these weights. Okay. Then I have LSTM cell. Uh, units is 30, dropout of 0.2, recurrent dropout of 0.2. Okay, so 20%. Then finally I have a dense layer uh, with input as 20 and activation as softmax. Right? So sorry, this is the output, like the classes which we have to find out. Input will be the output of the LSTM. Right? So this is what we have: embedding layer, right? 30 and 100 parameters. Then we have LSTM layer with uh, 30 inputs, 30 output, right? And input will be from here. And then we have finally a dense layer, which are it has output of 20, right? And these are different weights. So in LSTM, this is the number of weights we have, right? And in embedding layer, we have this many parameters. Now see this, like we are not training these parameters, right? This many parameters we are not training. We are training only this many parameters, right? So the process will be much faster. And here we are using RMS prop as an optimizer. Loss is categorical cross entropy, right? Matrix is accuracy. Why categorical cross entropy? Because there are 20 classes, right? And then we are doing model fit with batch size and epoch. I just change it to 2, so just we can quickly get the answer. Okay, I need to compile it, so let me compile this. Right. Okay, this is the same after 20 epochs. So we can see here the okay, the accuracy is not at all good. It's 27% only. Sorry, we can see epochs with 20. I'm not running it. It will take some time, but we can just see the accuracy. Final accuracy is 49%. Uh, and on the training dataset, it is 58%. So yeah, not so good. A lot of changes can be done. So what we can do is we can build a neural network with simple RNN as well instead of LSTM and see like how the performance is on this data set, right? On 20 Newsgroup. Uh, Second thing what we can do is to use the LSTM above without the pre-trained word vectors. So instead of using pre-trained word vectors, we can randomly initialize the weights and have them learned during the training process, right? So we can have this embedding layer, uh, and in this embedding layer we have this enable as true, right? And yeah, we can make the embedding layer learn the weights instead of using the pre-trained one, right? So you can see uh, how different that is, right? And the third thing which you can try out is try different sequence lengths. Like we use 30, you can change it to let's say 80 or so, You can also change the dimensions for the hidden state. So I think we used 5 per dimension. Oh, okay. We use 30, but you can increase it to furthermore. So these are the units, and you can increase these units and see how the improvement is. Right. Okay. So should be an easy exercise. You can try it out. Uh, any questions? Do let me know. Uh, okay. So I'm ending here. I'm ending this session here. If you have any questions or queries, do write me. We can discuss this in more detail. And tomorrow we'll go through, or in our next class, we'll go through final summary of whatever we learned in deep learning. So it is again, it is just basics of deep learning. We just covered uh, basics of neural networks, RNN, CNN, and LSTM RNN only, right? And we had gone through some examples of some uh, workshops on this data on this uh, yeah, on deep learning. So there are many other things which we haven't discussed here. So the new things which you can look is encoders, encoder decoders or auto encoders, and then there are RNNs with attention as well, which are the new research areas people are working on and using it in different applications. So we haven't covered that. Maybe there could be some applications which we can directly see, like how that application uh, can be done using this uh, uh, advanced techniques of autoencoder and attention. Okay. So I will take one more class where I will try to summarize the whole thing which we learned. Meanwhile, if you have any questions on this, do let me know. Thank you. Thanks a lot for attending this class.